Hi Roselle. I thought I would make you a video just to kind of explain my thoughts so far. I've been working on it, and I think I've kind of got a bit of a start on it, which is different than what we talked about this afternoon. Um, so I thought what I would do is just kind of think out loud a little bit and make you this video and kind of let you look it over and see what you think. And maybe you've done an example similar to this in class, and it might click and you can help me decide if we're on the right track or not. So here's my thoughts so far. If we have a grid, and let's start at the origin, and let's put our 1 kilometer distance here. So really the intersection is there, right? Okay. So what's happening is he's not going to intersect with the train, obviously. He's still a kilometer away. And as the drone changes paths, my assumption was when we were doing this, when we started out, that we were dealing with the Pythagorean triangle. But then when I tried to work with it, it kept kind of contradicting, like the equation wasn't working out. And I was like, well, wait a minute, that doesn't make sense. Because this is the starting point right here at the origin. And if he's, if here's the end of the train right here right now, then that would be the triangle. But because this side's not changing, this is constant, then as soon as the train's moved to here, now that's a triangle. And so this is a moving target, right? And so we don't know when it catches up, but you can see that it's not just one triangle if we were trying to do this in a linear way and draw a triangle. And so my brilliant son read the problem and said to me, no, it's a curve, right? And that makes more sense, doesn't it? Because if this is the path of the train and here's our drone trying to get there, then it's doing this, right? It's having to keep adjusting its path a little bit, sort of changing the angle a little bit as it's trying to hit the back of the train. And so what we're dealing with is a curve, or a curved path that the drone's traveling along. And then he tells you in the question that dy dx is, where's the question gone? Dy dx equals 0 and x equals 1. So if this is x equals 1, I know my scale's off a little bit there, I apologize. If that's x equal 1, then dy dx, which is the rate of change of this curve, dy dx is the slope of this curve at any point along the curve, isn't it? It's the first derivative, so it's the slope. It equals 0, which means it's a horizontal tangent line right there. And so the assumption is that we must have either hit the train already or we're hitting the train right there. Because if that's going to have a horizontal slope, that's a turning point. That's going to be a maximum, which means then our curve starts coming back down. Sorry for the poor diagram there. So that's what I have so far in terms of what we're looking at. And that's why I think I was confused with the two triangles, because I knew that something had to change, but it doesn't make sense for it to be a straight line hypotenuse. It has to be a curve, and I think the curve is a parabola, and I'm trying to figure out, it's an upside down parabola, right? So it's a y equals negative x squared, but the parabola also has a vertex. It looks like the vertex is at 1, 1. So that would give me this for the equation of our parabola. So if that's the equation of our parabola and we need the rate of change at any point along the parabola, then we could differentiate that. I haven't gotten that far. This is why it's good for me to talk this through with you, you see. So I'm just wondering now, if we try to differentiate that, are we going to get close to what he's got? I'm going to go back to the drawing board on the the derivative now and see if I can get close to what he's got. I think we're on to something here. But I'm hoping that maybe just talking this through with you and just sending you this so far to think about and kind of chew on, he may have done something similar to this in your notes, or maybe he will before Wednesday, and it might ring a bell and kind of all click, maybe, but we know he doesn't often do that. So let me think this one through a little bit more from this point, and you can think about it too, and then I'm going to get back to you again on this after I've had a chance to think about it.